Alright, you guys, it's Berkeley time, so we're going to start the presentation. So I'm Chris Liu. I'm a member of machine learning at Berkeley, and I'm going to be hosting this workshop called A Practical Introduction to Deep Reinforcement Learning. So basically, I'm just going to be teaching the basic ideas behind deep reinforcement learning and showing you guys how to do some basic code samples and read papers and implement them pretty much. So the first question is, what is reinforcement learning? I'm sure a lot of you already know what it is because you got the workshop and you want to know how to implement it. But here's just a nice video to illustrate some of the ideas behind it. So this seems pretty boring because it's just playing an Atari game. But I think the really neat idea behind it is that the agent starts out knowing absolutely nothing. It just gets a bunch of pixels and a reward score. So what's going on is it doesn't know what its actions do. It doesn't know what a paddle is. It doesn't know what a ball is. It doesn't know anything about this world other than it sees pixels and it gets points. The thing is, after enough training episodes, it's able to figure out some very good strategies to beat the game. And the really cool thing is that you can adapt this algorithm to play a lot of other different Atari games, or not even just Atari games. You can play a lot of different games in So an algorithm very similar to this one would be used for AlphaGo or for even the Dota or StarCraft stuff that's going on. And so you can see here that it's figured out the strategy of putting the ball at the top and getting a lot of points that way. And that's a long-term strategy. You would think that it would only learn short-term bouncing back the ball. It actually learns long-term what it should be trying to do. And so that's what's really amazing about deep reinforcement learning right now. And so you guys might have heard news about OpenAI and DeepMind doing all this cool stuff. And it's just basically a lot of these ideas in deep reinforcement learning. So I'm going to go over how do you even define the problem? What is a game exactly? And so this is how we kind of look at it in reinforcement learning. So there's an environment. In this case, it was the Atari world breakout. And you have an agent that gets some observation from the world. So in Atari game, it would have been pixels. And also a reward, which indicates how well it's doing. And it implements an action, outputs an action at each time step. So each time step, it sees a state and a reward, and then uses that information to decide an action. And so there's actually some criticisms on this, the world isn't a single reward. But in terms of these games, this is how we like to define it. So what's the goal then? The goal is to figure out how to play optimally, right? Given the pixels on the screen, what inputs should you put? And so when you play the game, how do you decide how to play? You want to maximize your score, right? You want to maximize the total reward that you get. So we define something called the value function. And the idea behind the value function is you want to maximize the total expected future reward. So it's not just the reward you get at this time step or the next time step, but you want far into the future the total amount of reward you expect to get. And we also want to prefer immediate rewards over delayed ones. So you want your reward sooner than later. It's just something that helps more cleanly define what value is, essentially. And so how we define value is, you see this function up there. So value of S, so the value of a state, S, is equal to the sum of the reward that you get times that hyperparameter we call gamma. So you can see that what's going on is the value of the state is the reward you can get immediately, plus this value, which is hyperparameter between 0 and 1, times the reward you get in the next state. So basically, slightly less every time. You keep re-multiplying by gamma. So that means the farther and farther in the future it is, the less and less value it counts as part of your state. But the whole idea is you want all the rewards in the future to count as part of your value of the state right now. So this is really useful, right? It tells us what we want to achieve. But it maps a value to a state, but it doesn't tell us what action we should actually take, right? Given this function, you don't actually know what action you should be taking. So instead, what we estimate is something called Q values. And so Q values return the value of taking an action A in a state S. So it's very similar and has a very similar definition to the value function, except the difference is we can now know what action we should take in the state, right? You do the argmax, so you take the action that maximizes the value, that maximizes the Q value of a state. Am I going too fast, or is this okay? Yeah? All right. Is there a question?
Yeah, quick question about the, so for the review values, you don't train it concurrently, right? You wait till it's done and then train it based on all of future values at once.
Yeah, we're going to go over how it trains in the next few slides. Yeah, this is just defining what these terms mean. But also I forgot to mention, if you guys can just get the materials and install them, that would be really useful for the next part of this workshop. So yeah, now we're going over how we actually learn these values. So basically what you would do is you would store the values in a table, and you would have your agent in this world, and you'd have it choose some action A to perform in the state. And then once it takes the action, it gets a reward, and it gets the next state, right? And then you would update your Q value in your table based on the reward and the next state that you got. So this is kind of like, that's like kind of similar to dynamic programming, right? You have this table, and you update it based on the other values in the table. But it's also based on the reward and the state that you got. So you see that this eventually over time will approximate the actual Q values of the state in action. So this is essentially how we do it. We would have the agent in the world. So when you saw the Atari video, for example, it was essentially doing something similar to this, just over and over again. And one important thing is this idea of exploration versus exploitation. So I said here in the previous slide, just choose some action A, but what does that mean exactly? So basically the idea is if your agent always exploits and does what it thinks is the best option, then it might understand the environment less. It might get more immediate reward, but it might be missing out on part of the environment where you might just never saw it and might have more reward. On the hand, if you explore, you get less reward overall, but maybe you might understand part of the environment better. So this image I got from the 188 slides, it's like if you went to a restaurant and it's a place where you normally go, you know it's pretty good, and a new restaurant opened, if you exploit, you'd be going to your old restaurant, and you think it's pretty good, but you never actually know whether or not that new restaurant's better or worse if you don't explore, right? So what we do is something called epsilon greedy action selection. There's better ways to do it now, but the idea here is that you would take a random action with probability epsilon. So just normally you would take the best action, but randomly you would take an action that's random, and you would decrease this value over time. So over time, your agent converges to the best strategy. Hopefully. So there's some shortcomings of this, which is these ideas seem like relatively simple compared to like neural networks and all the stuff that you see in the Atari video. And this is kind of where that stuff comes in. When you use tables, you can't actually use a continuous state space, right? You can't store infinite number of values in a table. It doesn't do very well in large state spaces in general. If your state space is very big, your table would also be like way too big. And it doesn't generalize, right? If you have two states that are very, very similar, in a table they'd be completely different values, but in practice you'd want them to have similar types of key values. So for example, in that video we saw, you would need the images are 84 by 84 by 4, and then there's 256 values per pixel, and you have 18 actions. So your table would need to store, I think like 130 million values, which is too many values. And you'd also not only have to store them, you'd have to like learn all of them. So that's just way too many values to have to deal with. So how would we deal with this? Neural networks. So neural networks are basically function approximators. So for this workshop, I'm just going to be saying that neural networks are a tool that we use where if you put in enough inputs and enough outputs, the neural network will approximate like any function. Is as far as I'm going to go for this workshop, but we can talk about that after the workshop. One thing is that you can't just replace the table with a neural network. We'd have to do something called experience replay. And the idea here is you want to be able to have an experience count like multiple times in your training. So in the previous training, we saw that if you experience something once, that's the only time you update it. But with experience replay, you can have your agent kind of remember what it did in the past and use that multiple times to train the neural network. So I'm just going to go over the code sample really quickly right now. Or not really quickly, but. So do you guys get the workshop materials? It's on the GitHub over there. And I'm just going to be going over the code here, line by line, so you actually understand what it's saying. So basically, first we import Gym. So Gym is this thing called OpenAI Gym, which I think would be really useful if you guys are interested in deep reinforcement learning. The idea behind OpenAI Gym is that they have all of these environments where, with all these reinforcement learning environments, where you can train your algorithms. So the one we're going to be working on is something called cart pull. And the idea is you would want to, there's a pole attached to a joint on a cart which moves along a frictionless track. And you get to apply force to this cart, and your goal is to keep the pole in the air for as long as possible. So Gym basically just is like a library for a bunch of these reinforcement learning environments. And then we're going to be using something called Keras. And it's a very simple and very convenient neural network library. And it's what we're going to be basically building our neural network with. Then we're going to be doing NumPy, which is just like a nice math library for Python. And then random, because we want to do epsilon greedy. So we want to sometimes take a random action. So this is how you would make an environment in OpenAI Gym. You would just say gym.make. And like I said before, the environment we're making is called cartpool-v0. If you want to make a different environment, you would just change the name there from cartpool v0 to like acrobat v1 or mountain car v0. And then here I define the action space and observation space. So here there are two actions, right? You apply an action of +1 or -1, and you get 4 values from the cartpool, which is I think like the speed, the angular velocity of the pole, and the angular, I think, position of the cart, or not position, but the position of the cart in space. Is there a question?
Yeah, could you zoom into them?
Yeah. So what's next in line is I define the neural network.
Do Command plus
Yeah. Thanks.
and turn on word graph color.
Huh?
There's a view word graph as well. Set it for the bottom.
Here we go, thanks. All right. So this is how you create a neural network with Keras. You just define, the idea is we want a sequential model. So you want one layer to feed the next one to feed the next one is the idea. And then we add these things called dense layers and activations in between them. It's like a very basic neural network where we essentially are going to use this model to train it and on inputs and outputs. Afterwards, I can go over more in depth on how we can change this to do more complex games. But for now, this is all we need to solve Cartpool. And so here's the code essentially that we saw, the pseudocode that we saw from before, where we define the number of episodes we're going to run for. We're going to have our epsilon value, which is when we randomly take actions. Anneal, which is how much we decrease epsilon each episode. The experience buffer we're talking about. And basically the discount factor, which is how much we prefer current rewards over future ones. So we start by resetting the environment and getting our observation. And then we know that we're not done yet, and we want to keep track of the total reward for the episode. So while we're not done with the episode, we're going to do this, which is epsilon greedy. So you randomly sometimes take a random action, which is between 0 and 1 year. But in the event that you don't randomly take an action, then you want to take the best action. So we take the Q values that are neural network outputs from the observation, and we take the one that has the maximum Q value, essentially. And so that's the action that we take. So here, it would be the maximum Q value, and here's just a random action. It depends on whether or not we decide to take a random action, that kind of stuff. And so now in the environment, we decide to take the step, next action. And what this function does for the environment is it returns the next observation, the reward, and whether or not you're done. And so we get the next observation, we increase our reward count for the episode, and then we add this to our experience buffer. So this is what we need to update the agent, right? We need the observation we got, the action we took, the reward, and the next observation, essentially. And here, every 10th episode, I'm going to have it render so you can watch it go. So now, this is the training part. So basically, what's going on here is we're just reorganizing, we're getting data from the experience buffer and feeding the inputs and the outputs and training the neural network with it. So here we get a random sample from our experience buffer. And then we basically, these are the inputs that we want to train our neural network on, and these are the outputs that we want to train on. We're going to just create this empty list first. And then, so for each state action for tuple here, inside of our mini bash, we want to just process the data so that it works out. So here, the input to our neural network was the observation, so that's what we're going to train it on. And then the output is this right here. So what's going on here is that we're regenerating the Q values for the observation, and then just replacing the one for the action we took with this, which represents the reward plus gamma times the max reward of the next state. So you guys remember like the equation from before, the way we define value is the immediate reward plus gamma times the next one. And that's what's going on here. It's the immediate reward plus gamma times the next one. And yeah, so once we do that, we append that to the outputs that we want, and then we just fit our model on the inputs and the outputs, and then we decrease epsilon. So there's like a lot of extra lines here for comments and spacing. I think in total this would be maybe around like 30-ish lines of code, which is pretty cool considering it's able to solve some tasks. So if you run it, you can see it go. So what's going to be printing is the reward for the round, I think. And it's going to be rendering the video every 10th episode. So you can see it's doing pretty poorly. There it just stopped. So when it stops, it means it just died, essentially. But you can see the reward over time is slowly going up. So it had a perfect episode there. And you can see that's learning pretty quickly. So you learn pretty much how to do it, more or less. You can see it's getting slowly better at balancing. So if you guys have the code, you can just run it, and it should work. Yeah, so see there, that's a full episode, I think. So 200 is the max score, and you'll see that over time this will eventually consistently hit 200 as a score. So the reason why it's not, the reason why it's able to hit 200 sometimes, but it doesn't always hit 200, is because it's sometimes taking those random actions, which is what's making it die. But this environment is relatively simple, and it's like nothing like the Atari one where you have pixels and everything. But the thing is, the really cool thing about this is, if you wanted the code to work in Atari, all you really have to do is add something called convolutional layers here. And basically, you change the observation space and the action space. But all you do is add these convolutional layers to a neural network, and the rest of this code should pretty much work almost exactly the same. And it should work on Atari methods. The reason why we don't do it here is because it would just take way too much time to train it. It might take like a day or two. So yeah, we can't do that here. But over time, yeah, so you can see here, it's consistently hit 200 for a while here. So we're going to go back to the slides. So yeah, we can go a little bit more in depth in the code after the presentation. But one thing is that I just went over something called value-based methods. There's other methods that you might want to look into in reinforcement learning called policy-based methods. So here we went over the value of taking a state, taking an action in a certain state. But instead what you can do is you want to directly learn what action to take in a state. And there's a bunch of papers on this you guys can look into, where you can just learn what action to take directly rather than looking at the Q values. But I'm not going to go into that too much here. So from here, we can actually just add a lot to our code and basically implement papers that came out pretty recently. So I'm just going to go over a bunch of papers we can maybe try to implement. And yeah, so the first one is human level control through deep reinforcement learning. So this was published in Nature in 2014, and this paper is what caused deep reinforcement learning to become really popular. And it introduces an algorithm called DQN. So our implementation is most of DQN, except DQN adds something called a target network. And what a target network does is it essentially is an old snapshot of the neural network, and it helps stabilize the values. We can go into implementing that after this. So you can actually read the paper, and it should be very readable. None of the math is particularly hard. We've essentially seen this equation before. Yeah, and you can see how the scores do better over time. And here is how it does on all of these different targets. So this is a single algorithm. They don't adjust any of the hyperparameters. They don't do anything. And you can see that it does better than humans at all of these games. Ice hockey, Qbert, pinball, breakout. And the really interesting thing is they even compared it to the amount of time it takes a human to play the game. So they let the agent train, I think, for like 2 hours. And they also hired humans to play the game for 2 hours, and they compared the scores, which is how they got these numbers here. And yeah, so we can implement this after. Another improvement in September 2015 is something called double Q learning, where you use this target network I was talking about to estimate the Q values. and then use the other network for the actions you want to take, and this just helps stabilize the values. We can implement this one pretty easily too. Another improvement is dueling networks. So these, you can just click the links and read the papers. They should all be readable. That's the really cool thing about VBRL.
Oh, sorry.
None of these papers are, like crazy, or a lot of these papers aren't like super crazy in math. And they should be, we should be able to read them and at least kind of understand what's going on. And the idea here is that you want to estimate the value of a state and the change in value of taking certain actions differently. The idea here is that if you're in like a really good state, all of the actions you take are good, so how do you know which one you want to take? So the idea here is you want to see like which action actually improves my value rather than which one is just has the highest value. And then here's another one that came out in June of this year, which is pretty cool. It's only like a couple months ago. And it's called parameter space noise for exploration. And here, we did epsilon greedy exploration, but they find that it's better to inject noise into the weights of the neural network rather than just having it randomly take actions sometimes. And they found that this leads to better exploration, and they just show that they just do better on all of these benchmarks and stuff. Here is a paper that is very, very new. It's currently under review, I think, for iClear 2018. We're not going to be able to implement this one because it requires a lot of resources. But basically, they use something called prioritized experience replay, where we have the experience buffer, right? And we randomly sample from it. But what they do is they sample from it based on how much they think they'll learn from that particular experience. So you can see here that it does way better than like what we can do with just normal DQN. Obviously, this is like kind of an unfair comparison because the amount of computation, like the amount of resources they have is a lot more for running the game on like a large number of threads, essentially. So I'm just going to go over what's currently going on in deep reinforcement learning and some stuff you guys might be interested in looking into. One of them's called hierarchical reinforcement learning, and the idea here is that a lot of problems in the world have structure to them, right? You want to achieve this goal, and to do that you want to do this, and you want to achieve another goal. And to do that you have to take these series of smaller actions. So that's what's going on in hierarchical RL. We break a problem down into goals and actions, and so, or sub-goals and actions. So you would have one agent kind of assign a goal to like a controller agent, and that agent should figure out how to achieve that goal. Another one's model-based reinforcement learning. So the idea is that if your agent can predict the future in the environment, or can like model the environment, they might be able to learn it a lot better and a lot faster. And maybe if you make a small change to the environment, the model might be able to pick it up faster than just readjusting all the key values. And I think it's improved exploration. Like before we saw parameter space noise as one way to improve exploration, but there are a lot of other pretty cool ways to look into exploring. And then another one's benchmarks and environments. So we can see that OpenAI is moving into Dota right now. DeepMind is doing StarCraft. And the reason why we're moving on to these other environments is because we're already superhuman on Atari games. So if you do better on an Atari game, like what does that even mean? Does it mean like your agent is more intelligent, or it doesn't really mean too much at this point. And there's still some more multi-agent reinforcement learning. You want them to be able to learn, like maybe like what to do in social dilemmas, like prisoner's dilemma, or that type of thing. There's memory and attention. Right, so this neural network doesn't have any sort of memory between time steps. It just takes an observation, outputs an action. But if you want to remember, what happened in the past, then you need to make some changes to your neural network, essentially. Transfer learning and K-shot learning. So if you have an environment and you make a small change to it, you want your agent to be able to, learn those changes faster. And finally, competitive self-play, and this is what OpenAI did for their Dota bot, where they had an agent just play with itself for a really long time, and it did really well. So takeaways is DeepRL isn't that complicated. I mean, you saw it's only like 30 lines of code with these libraries, and there are tons of papers that you can just read and implement. So I think I'm just going to first do questions, and then afterwards I can just go over and implement some of these papers with you guys. Are there any questions, or did I go too fast? Yeah.
For the when you're talking about I think it was experience replay.
Yeah.
Do you mean they go through the environments again and try to learn from them again, after improving the code, Like, how does that work?
Right. So kind of what's going on is we're storing the transition. So we're not really like going back physically and having the agent go back and take those actions again. What we're doing is we're having the agent remember, oh, when I was in this state and I took this action, this is what happened. And basically that's all it needs to learn, right? It doesn't actually need to physically be in that scenario to actually learn that stuff. It just needs to remember that it happens, that this transition happens, and it can update it that way. Are there any questions? Yeah, in the back.
Where is experience buffer actually used?
Okay. So here I have experience buffer. So here I append the tuple. So this is the observation that we got from the state. This is the action that we took. And then, so this is what we need. This is essentially the entry into the table, right? Observation and action. And then the reward and next observation is what we got after taking that action, and whether or not we were done. And so here, we sample from the experience buffer to get like a random mini batch from the experience buffer. So now we have a bunch of these random tuples of observation, action, reward, and next state, essentially. And we basically go through here. We unpack the samples, essentially, and calculate what our Q values should have been, given that this is what we saw. And then we use that to train the neural network. Did that answer your question, or?
Yeah.
Okay. Yep.
Why do we only go through the second block of code if the length of the experience buffer is bigger than the batch?
So, I mean, this is just to make it easier for me. If the experience buffer is smaller than the batch, I can't randomly sample batch size. Another reason for this is kind of what people start with normally is completely random actions for the first couple episodes. And this doesn't really do that, but it doesn't train the network, so it's kind of like random actions, but not really. Right, and the reason we do this is because the agent doesn't actually know what the rewards are like in the very beginning, so we don't want it to use that information. Because it's just random information. Yeah.
Clarify. You're not doing any. You're not, shall I say, handling the neural network in any sense until the second. Well, not done. You basically.
Yeah. So
So
here,
you're basically trying to do the Q exploration. You're basically doing the classic Q exploration.
Yep,
So
exactly.
network- No involvement in your network until the second piece.
yeah, exactly.
Until you're almost done.
So we use the neural network to figure out what actions to take, but we don't train the neural network until the episode's over.
Yeah.
I mean, you could do it after every time step if you wanted to. This is just how I do it here.
Just say computation.
Yeah. Neural networks are better trained in batches and stuff, which is why I do it like this. Are there any questions? Yeah.
Does it behave differently if you use a different neural network?
Yeah. Or sorry, what were you saying?
If you use a recurrent one or a convolutional?
Yeah, exactly. So this one is neither recurrent nor convolutional, and the idea is the people in the Atari paper, they added convolutional layers, which is what made it work, right? They added convolutional layers because they work better on images, and because they fed the agent the images of the screen. In this case, I'm not feeding any images. I'm just feeding a bunch of values. So that's why I don't use convolutional networks. And then recurrent networks are pretty cool. They give the agent kind of memory in between states, right? And that's really useful. It just makes it a little bit harder to train, but that's an active area. Yeah.
If you wanted to play a game like Tetris, which has, you have to look really far ahead, and essentially the rewards are very opposite, so how would DQNs manage that?
Right, yeah, so that's actually another active area here. I'm going to go over a short part of a presentation from something else really quickly to show you guys. The idea here, kind of like what you're saying is, there are a bunch of games that you can see it doesn't do very well at, and I imagine Tetris would be one of those, because here we can look at this video. This is a game called Montezuma's Revenge, and you can see that the reward doesn't change for a very long time until he goes and picks up that key, which is a lot of time steps compared to something like Breakout and Calm. And you can see he has to learn all these actions in a particular sequence without any sort of reward supervision. You see he has to jump over the snakes. The DQN agent wouldn't know that snakes are bad to start with. It doesn't know what a ladder is. It doesn't know what a key is. It doesn't know what a door is, right? And so we take advantage of this going in when we start playing the game. but the agent actually has to learn, you know, what all these things really kind of are to start with. Yeah.
It only starts with the fact that 4 points are better. That's literally what it starts with.
Yep.
Everything else. Yes.
Yep, exactly. It doesn't even know that that's its agent. It doesn't even know that, you know, pressing this button moves them left or right or up or down. So yeah, for Tetris, it's kind of similar, right? You don't get rewarded until you clear a whole row. And even then you want like some type of long-term planning there. And so like here, what they do is, maybe hard goal would work for Tetris, I'm not really sure. But this is kind of what I was explaining before when it came to hardcore RL, where you have, you know, this manager and a worker. And the manager is kind of like his own agent, where he takes an observation of the state, but rather than actions, he updates goals. And the worker is also kind of like an agent by himself, except instead of just an observation, he also takes some goals and then updates an action. So this whole thing right here is what makes up a single agent. And the neat thing about this is that it breaks down this problem, right? No longer is it like you have to do all these actions before you get a single reward. Now it's you have to do all these couple goals to hit a reward, and for each goal you only have to do a couple actions. So the problem gets broken down into this type of structure where nothing is like no longer that far away. So for Tetris, maybe something like a hard goal push would work. Maybe normal DQN would work for Tetris because the reward isn't that sparse, right? You sometimes do clear rows randomly. And if it learns how to do that properly, like we saw in the breakout example, it learned the proper strategy of having the ball go to the top. Right? And that's like a pretty long-term strategy. Any other questions? Yeah?
So how would you, like, if you're doing like hierarchical RL and you are assigning, so what do the goals constitute? Is it like some like how would you like consider a goal? Is it a certain change in like the pixels or something like that?
Right. Yeah, exactly. So there's a couple implementations of it. Here's one of them. Here the guy just hard-coded the goals in Montezuma's event. He's like, oh, okay, if you hit the ladder, then that counts as, you know, one of the goals. So you pick up the key, that's a goal. You go to the door, that's a goal. This kind of feels like cheating, right? Because you're giving it external information. So then these things called feudal networks, which are kind of like what you're saying. It creates this like internal representation of the state, and then it defines the goal as a change in this internal representation. Like you're saying, like a change in the pixels or something like that, right? There's essentially what's going on here. So yeah, these are two different ways to implement hierarchical RL. So this one, the criticism is you're hard-coding information in. And this one, the criticism is mostly that it's like very contrived kind of. The model seems like they explain why they came up with all these design decisions, but it's very complicated looking, and a lot of people are like saying that like, oh, like, this doesn't really add anything. They just do like a lot of like nice tuning. Yeah. Any other questions? Yeah.
Like, could you apply like deep reinforcement learning to like a casino game like Blackjack, or is it work as like the same action you would win one time and lose another time?
Yeah, no, it would work perfectly fine. Yeah. So I kind of skipped over like the probabilistic elements of reinforcement learning here, but yeah, like the algorithm takes into account these transition probabilities and stuff. Right? What are the odds of something happening? If you have enough experiences, like they kind of balance out, right? And so that's what's going on here. It will take that action, you know, 100 times in the state, and you know, 70 times it'll work out well, 30 times it won't. So it's like, okay, that's pretty good, right? Yeah. Any other questions? All right. So I'm just going to be implementing target network now, I guess. So we can read the paper and you know, see what they say it is and why they need it, and then just implement it. So do sorry. Okay, so they're saying reinforcement learning is unstable or even diverges when the neural network is used to represent the action value. There's a lot of reasons for this. Correlations present in the sequence, and the fact that the small updates to queue may significantly change the policy and data distribution. So the idea here is when you use a table, the values are completely separate, right? When you change one value, you only change that. But when you use a neural network, you actually change, you know, the other values nearby. So the idea is that when you play a game like Breakout, one state and the next state are very close to each other in terms of pixels, right? Like sequentially. And so when you update one value and then you update the next one, you might end up kind of just exploding this value because you just keep adding over and over to it. And so what they do is they use something called the target network. see if they like cleanly define it anywhere. Yeah, so here. So they mentioned two modifications. The first one was experience replay, which I was talking about before. And the second one is the target network. And so they essentially, every C updates, they clone the network to attain a target network. And they use that for generating the Q-learning targets. And so they say this makes it more stable. So you can just use this information and just try to implement it, right? So here we want to be able to clone the network, right? So we could just say, can I find a function that clones the model or something? And so if you pass in a model, we'll clone it, but if we don't pass in a model, let's just copy it. And if m model dot set, I don't remember the exact words for this, but or exact functions, but I'm just gonna guess. And then now we can just say model equals make model, and then we can say the target model is make model, except we want to copy over the weights from the rest, right? And then we want to update target, like let's say like every 5 episodes or something like that. It'd normally be a bigger number, but this is Cartpool, so it's like a very small game. So having too big of a number of target updates, I guess, would be pretty bad. And so here, we just say, we add in here like, if I, which represents what episode we're on, mod, how often you want to update the target, is equal to 0. Then we want to say that T model is equal to make model. So we want to just recopy the weights in again, right? And then what they say is that they use essentially this to generate the values. So here, instead we just replace this with T model, replace that with T model. And that's really, I think that should work. It's probably not going to work first try because that's how these things go, but you can try it. Okay, so you see here it pretty much perfected the Cartpool environment. We got 200, which is like the max score. So if we want to run it again, let's see if it works this time. So, I mean, I don't have evidence that here for this particular environment that shows that the target network learns better. But you can see that the scores for on Atari games do a lot better. Let's see. Oh, not there. Okay. Where's the PDF of this? So here. So here they have with the replay and with the target network, it gets these scores. With the replay without the target network, it gets these scores. Without the replay with the target network, it's these. And without either one, it gets these. So you can see it does really poorly without either one. With the experience replay, it has a huge improvement. And with the target network, it has not as big, but still a very significant improvement. And then with both of them combined, it does a lot better. So yeah, that's that. So then we can just go on to the next paper and try to implement that one, I guess. So this is double Q learning. So the idea in double Q learning is they just found a very small way to improve the stability of the neural network. So like I said before, two states when they're very close to each other, and you update one of them, you might actually end up affecting the other one when you didn't want to, or you might end up blowing up this value for the network. So what they do is they want to prevent that overestimation. And so what they do, okay, well the paper is not loading for me. Nope, never mind. Right. They write it like this. So actually that's not particularly clear for you. let's see. So the idea of double Q learning is to reduce overestimation by decomposing the max operation of the target into action selection and action evaluation. So you saw here, all we did was we just took the max of the we took the max of the we took the max of the from the target network, the max Q value. But instead, what they're suggesting is we want to separate finding what action we would have taken with the value that we're getting. So instead, we're going to say, okay, the action we would have taken in the next state is actually going to be the argmax of the Q values from the next state, right? So now instead of multiplying by np dot max of this, we actually just do np dot max, or we don't do np dot max. We take what we outputted, and we want the value that corresponds to the action. I think we should do that. So we use main network select action and target network to get value. So the idea here is that we now separate it out. So before we took the best action you would have taken with like an old snapshot of the network, but now we're taking what action you would have taken with that current network when we train it. Yeah, I mean, I might be going a little bit too fast in explaining these things, but you guys should read the papers and they should be pretty clear. Yeah?
So can you just quickly show the code that you used for the last one?
Yeah. So here,
Or in the middle, or any other, yeah.
the code we introduced in the last one, like for.
Just, I can copy all those.
Oh, okay, yeah, sorry. I can add this back to the. I can just push this back up to GitHub.
Thank you.
What were we saying?
So the network returns a prediction for the reward for going left and the reward for going right for each option, for each potential experience, right?
The reward for going left and yeah, exactly. Or not reward, but value, right?
So like the total long-term value time discounted back to the present.
Exactly.
Can you explain the structure of Q vals and like where we're inserting this value?
Right, yeah. So what's going on in Q vals is, so normally you saw on the table, like it was, you get from the state and the action something back, but the way we built the neural network is a little bit different. We put in the state, and it outputs the Q value of every action. So we do this because it's just a lot more convenient when writing the code. We can just say the argmax rather than having to query it a bunch of times for each action. Yeah. Sorry if that wasn't too super clear.
And we're always putting it in the 0th element of Q vals?
Oh, right. So Q values is like, I think
This is down on line 90.
line 90. This one?
Or 99, yeah.
Yeah, so what it outputs is actually like a 2D array. It's just the way cross works. It's because like you might want to predict on like multiple things at a time. In this case, we're only doing one, so we just get the first one. But the idea is if you like predict it on multiple things or use the model for. Oh, this is. Sorry. Wait, no, that is right. Yeah. So that's pretty much it. Yeah. It's just the way cross works. It's just reshapes and it's just shapes and stuff.
Okay. So it's always just returning one observation, but like that observation is nested inside another array?
So always returning one observation, but that observation is nested inside it. Actually, sorry, I misinterpreted. Sorry, I thought this was another part of the code. Sorry, this part of the code is actually saying that Q values is a list. And okay, sorry. So Q values and Q vals are different. So
Yeah.
yeah,
Q
you're right.
vals.
So Q vals basically only change one element in it because the model outputted this like 2D array. But we only need actually one dimension essentially.
Okay.
Are there any other questions?
Sorry.
So yeah, I mean, if you guys are more interested in this stuff, you can try implementing these other takers. They should be pretty readable and pretty implementable. And over time, you can just get better and better and hit the state of the art. This field isn't that old, which is really cool. This stuff came out like 3 years ago, which is when DQN came out. And so yeah, you can catch up pretty easily to what's going on in the field. Yeah?
Could you explain why you need a gamma? Like, why do you need this company for stuff?
Right. So basically, what people say is because you want to get more immediate reward more quickly. But another thing is that it actually stabilizes the key value. So you imagine like if you're taking like 16B or E16B or no. Okay. So the idea is that since gamma is less than 1, as you take like the geometric series, right? It doesn't. It's limited, right? It's bounded. So that way, the Q values are like bounded. Because if you picked 1, and let's say your episodes went on forever, right? Then every Q value would just be infinity, right? And so this kind of bounds the Q value. So it helps with like stability and stuff like that. Now, if you pick a number greater than 1, then that doesn't mean anything, right? Or you prefer it more in the future compared to right now. It's kind of cool. Yeah.
Can you explain how the gamma is used in the code?
Yeah. So here.
Yeah.
So here, I didn't explain the if statement. So if you're done, there is no next time step, so you don't actually incorporate the reward from the next time step, right? But if you're not done, then you incorporate the reward from the next time step. So what's going on here is that we're taking the action from the next state, right? And we're taking the maximum Q value from it. And so that's essentially the value of the next state for us, right? And so when you multiply by gamma, you're just discounting the value of the next state, which is essentially exactly what's going on in the equation. So if you look in the slides here, we define value like this: immediate reward plus gamma times the next one plus gamma squared times the third one. But in practice, what we do is we just estimate it, because it's kind of like a dynamic programming type of thing, where you have the value of the next state. So you just multiply it by gamma. Then I'll make that very clear. So you are essentially, you can kind of look at this as like a recursive kind of equation, right? It's the value of the state, which is the immediate reward plus gamma times the next reward, et cetera, et cetera. But if you instead just put the next state here, replace this R2 with the next state, you can say it's the immediate reward plus gamma times the value of the next state. And you can see that this essentially does the same thing. And so that's what we're approximating when we use DQ, when we use Q networks, so Q values. Any other questions? Yeah.
When you're making the target network, why do you make it a new model every single n time step?
Yeah, actually you're right. I could just I could just copy over the weights. Yeah. You're right. I could go in here and just say weights. Yeah. Yeah, there's no particular reason.
Okay.
Yeah.
And where do you use it further in the code?
We use it here. So here, we use it to generate the Q values that we, or not generate, sorry, get. So you see here, we do a recursive type of thing, right? We grab the next state, the Q value of the next state. So here we use the target network essentially to estimate this one. So remember I said before, when you update one state, you might accidentally update, another state that's very similar to it. But when you have an old copy of the network, that doesn't happen, right? When you update a state and then you use the old network to update it again, you didn't affect it with your last update, which is good, right? There's no longer this explosion of Q values. Any other questions? All right. Well, so at the end I have just some extra videos of some cool stuff that you can do with reinforcement learning. Here's an agent playing Doom. Right, so again, this just learned from pixels. Actually, this one didn't, but yeah. But it's still very impressive, right? It doesn't know what a bad guy is. It doesn't know exactly what its actions do. It doesn't know. It has to learn, picking up guns, the different types of guns, how to use them differently, all that stuff. Yeah. So, and then of course there's like AlphaGo, which happened a couple years ago, I think. Yeah. So just overall, I want the big takeaway from this presentation to be that DeepRL is not very complicated. The code you guys saw is not very long, it's pretty short. Implementing these papers isn't necessarily that hard. I mean, some papers are very difficult, you have to do some stuff, but a lot of them you should just be able to read them and implement them pretty easily, which I think is what's really cool about the field. You can just kind of participate in it, and yeah. And if you come up with your own ideas, maybe related to these things, right, you can contribute to the field, and that's pretty cool. That's really it. Are there any last questions, or? Actually, let me push the code. Right, well that's really it. Yeah, I'll finish it a bit. Oh yeah, yeah, you can see my questions.